Good evening, popular astronomers. It is Pop Astro Live. It is wonderful to have you along on our new slot Tuesday night. We're just going to play the theme music while everybody joins the stream and start sharing the stream. Please start hitting the share button right now, right this instant, while we play the countdown music. And you never know which person this may land in front of on their timeline. You might trigger a lifelong love of space. Good evening, popular astronomers. It is Tuesday, the 31st of August, 2021, and already there are 2 comments flooding in. Let's have a look. Good. Ian Morrison. Well, he's only got 1 R in his name, so that can only be the one and only Ian Morrison. And what a delight to have you along. Mr. Morrison, are you coming to Sligwee with Mac Astro in a couple of weeks? Is it this weekend? I might need to rejoin Mac Astro. I've seen an email about it from Malk about it being this weekend. Yeah, I'll just do a bit of life admin at the start of my show and ignore everybody else. It's fine. Kath is back! Yeah, well done. I look like I'm celebrating St. David's Day, but someone was selling these on their store the other day, and I do live in Anglesey, and I was rather smitten by it, so... Do you think they've got space for me, Ian? Can you find out for me? Can you get onto Steve Warbis, please, and find out if they've still got my little bedroom that I like, please? Good evening, everybody. Ian, that's a sad face. Pourquoi? Hi, Vicky. Now I don't know my Tuesdays from my Fridays. No, I don't know either. I've had like a weird Friday feeling all day. So basically tomorrow, it's the weekend. We've already had a bank holiday weekend, so we're already messed up. Hello, lovely. I can make Tuesday evenings. That's so nice to have you back in the chat room, Kath. I've missed you so very much. My little heart cries for you every single night when you don't join us. It goes, where's Kath? Where is Kath? Okay, so, oh my God, you never guess what I got. Right, how do we do this? Look what I got. Plug the mugs. Plural, plug the mugs. Plural, plug the mugs. Look, I've been sent new Pop Astro mugs. Thank you very much. We've got no room in the cupboards, but it's fine. We'll just have to evict some of the really cheap floral mugs that somehow we've managed to pick up from somewhere. So this is beautiful. Available. Thank you, Paul, for sending me these from the Pop Astro shop. It's very glossy, and you can drink it left-handed or right-handed, and you can have any beverage you fancy in this. I'm a particular fan of this one, and I know Sonia likes her one because it's the gradient. It's the colour gradient, isn't it? It's very astronomically inspiring. I've got stars in my eyes, or is it a ring light? It's a ring light. Oh, we've got this one. Stirry, stirry night. Are you stirring? Yes, because I'm stirring my lovely, lovely, lovely Pop Astro Live mug. And of course, let's not forget the basic Pop Astro Hardcore Edition. I love Pop Astro so much that I don't even want an astronomical image on the side of my mug. I just want, give me the logo, give me the logo. So tonight's show is a little bit different. Sonia has gone on holiday to Neptune. She's just sent me a quick postcard which got blown here by Neptune's supersonic winds. She said she's having a lovely time in the great spot. Lovely show for us this evening. We have got binocular. Well, first we've got Eleni with the space news. So it's all gone topsy-turvy. We're on a Tuesday night and we're starting with Eleni. And we've got 3 mugs. What a wild world we live in. Then we have got a binocular astronomer and close contender for my favourite astronomer, Steve Tonkin. Steve, I wrote you a song. I did, honestly. It's coming up in a little bit. Here's Steve's blurb that he kindly sent me to save me from doing any work. For millennia, people have wondered about the misty patches in the night sky, which became called nebulas. Clouds and the advent of, sorry, I've completely misread the punctuation in that, which became called nebulas. Clouds and the advent of the telescope merely increased the number we could see without adding greatly to our knowledge of what they are. The true nature of these enigmatic fuzzy blobs has only been known for a century or so, and they reveal a tremendous amount of information about the life and death of stars, the structure of the Milky Way galaxy, and the nature of the universe itself. Okay, so it's oh great, I've got my pub quiz collecting mug here. It's a virtual £1 to enter the pub quiz, and I will be around later with my invisible raffle tickets. Tell me how many you want in the comments, and we'll stock you up on raffle tickets. Top prize in the raffle is a 3-way trip to the moon and a kiss off Cosmo. Where is he? Why have you never thought of putting Cosmo in the mug? Does he fit? If he bursts open now and his little lavender beads go everywhere, we'll all be in trouble. He looks like a Dalek. Is it? Okay, the pub quiz is going to be split into 3 halves. We've got 2 lots of 5 questions, fastest finger first, and Cosmo's round at the end. And teams are strictly limited to 1 player per team. Robin, please can you keep score of the pub quiz, because I'm not very good at doing that kind of thing. Okay, so we're going to... I swear I can smell burning. I mean, Cosmo does go in the microwave. There's definitely a kind of pong up there. Maybe someone's burning a caravan or something. Right, let's have a look at the comments. Hi, Vicky. Great new time slot. Samantha and Nigel. It feels good, doesn't it? Great little bump to start the week. Ooh, loving the mugs, says Kath. Love the mugs. Look how excited new merchandise makes me feel. It's the dopamine hit of the novel. I can highly recommend it. Order as much as you can from the Pop Astro store. Daleks rule. They certainly do. There are only 11 coming. I will email Steve. Oh, yeah, I am going to join. I am rejoining, by the way. If it's this weekend, I'm all up for it. That's so good. So, good Lord, it's coming up for like 18 months. Obviously, it will be. I think I've lost count of the months. Every couple of months with Macclesfield Astronomy Group, we would go to a centre on the other side of Anglesey, renowned for its dark skies and communal kitchen, and spend 2 or 3 nights with the Mac Astro crew. So many long-lost lovely friends there. I'm really looking forward to giving Ian Morrison a big snuggle in his Berghaus fleece. Yes, he gives good hugs, that Ian Morrison does. Okay, right. It's definitely burning. Right, well, none of my plugs are on fire. It's got to be coming from outside. It's got to be coming from outside. Jed Mack, you are a superstar. Do you know why? Because last week we had Adam's second chance guest. That was our special last week. It was about Adam Morgan and his educational fund. Adam has been given a new cystic fibrosis wonder drug and is off to do all sorts of fantastic space-related education. Off the top of my head, I don't remember. And when I checked the fundraiser today, Jed Mack, who you can see there, who is also one of the biggest fans of the show, he's put 50 quid in, and that was really, really kind. It warmed my cockles. Pop Astro power. Thank you so much for that, Jed. And I know Adam's watching tonight, and maybe Jason. Here's a big kiss for all of you. Thank you, gentlemen. Okay, right, over to the pub quiz now. Eleni, I'm already running behind, to be honest, but it's hard to know how long these things are going to take, and I don't have a producer in my ear, so I just have to do it all on my own. Okay. We are going to go to the pub quiz now. So the way it works, there's a delay on this software. No problem. Thank you, Jed. There's a delay on the software. There's a delay on the internet. Everybody receives it at slightly different times. There is no satisfactory way to police an astronomy pub quiz. So all we're going to do is I'm going to read out 5 questions, and it's fastest finger first. Whoever pops up on my comments the first gets the answer correct, and I'll try my best to keep score, but it could go awry and there could be a battle of points. Who knows? Okay, are you ready, popular astronomers? Get your fingers warmed up. Do a bit of that, bit of that, bit of that, bit of that. Okay, 4th of January, which meteor shower? 4th of January, which meteor shower? Who's going to pop into the comments first? Ooh, hey, Eleni, but you are an employer of the an employee of Pop Astro Live. Well, you can have it anyway. Good girl. Yeah. Eleni definitely came through first then, but well done to David Digan who got it right as well. Oh, the answers are coming in. Paul Sutherland, well done on your pithy comments. Well done, everybody. Right, I'll write Eleni next to that. Eleni. Now, some of these are, it's your favorite shower. Good work. Oh, that's sweet. That's sweet. Some of these questions are hard and some are easy. It's nice to give everybody a chance to answer them. As I've discovered from being an astronomy quizmaster for a couple of years now, it's nice to give everybody a chance to answer. So if some are a bit easy for you and you think, piffle, these are way too easy, I can only apologize. Wait till the tough ones come along and then you can release your dopamine from the correct answer. Okay. According to the International Astronomical Union, how many constellations are there? Curtain shower. Shower curtain. Oh, all right, Paul. You get 0.1% for spelling it correctly. Mr. Numbers. Of course, Mr. Numbers is always going to get that one right first. Mr. Numbers. Look at all these. Two shapely ladies. Two ladies wearing corsets. Two pairs of glasses on the side. Two egg timers. It's 88. And Mr. Numbers got that one correct. Okay. How far is one astronomical unit to the nearest kilometer? Off you go. No way would I ever get that one right. Just no way, but doesn't matter. Paul can have it. I was only playing around. You're so sweet, Eleni. That's so sweet. Don't let him intimidate you into giving away his points. I know what he's like. Mr. Numbers really is Mr. Numbers. That is the answer here. Oh, and by the way, if you're Googling these, Cosmo bites my face. So don't Google them. What is the point of cheating? That snuggle can very easily turn into a very aggressive bite if you're Googling the answers. Ray, I'm sorry, it's wrong. Ian, he's definitely Googled it. What? Cosmo's going to bite my face because of you. Get off. Right. People are Googling the answers. There is just no way. Anyway, quick typing isn't easy. You need to do the quick brown fox jumped over the brown sleeping sloth more frequently, Robin. Okay. Well done, Mr. Numbers. He really knows his stuff. What happens next in the year 2062? What happens next in the year 2062? Let's write Mr. Numbers down next to that one. He really is Mr. Numbers. Thanks. Oh, Eleni got it wrong. Sorry, love. Oh, let's have a look here. Oh, well, the first one in my inbox was this. No, I'm sorry, Sandra. It wasn't you. It was not you either. Oh, the comments are jumping. It's hard to click on one because they jump. It was the Sky by Eye. Hallie returns. Well done, the Sky by Eye. I'll just jot that next to you. So far, Mr. Numbers is in the lead with 2 points. Right, bit of a brain twister for you now. Which planet has the 4th largest planetary mass in the solar system? Which, do you like my new floral cushions? I thought they really beautifully match this striking backdrop I've got. What? Mr. Bean gets his constellation. Sadly, no. He's going to be getting it in the year 2081. Oh. It's the planet that I've said wrong a couple of times here. It trips me up. Ian Baker is correct. No, the comments are jumping. No, the comments are just scrolling away up past the top of the screen. Ian, you were correct. Well done, Mr. Baker. You got one correct at last. It is Uranus. It is Uranus. It's weird, though. It's the 4th largest planetary mass, but the 3rd largest radius. What a crazy solar system we live in. Ian Baker. So the scores on the cosmic microwave background are Mr. Numbers 2. Eleni got 1. Ian got 1. I think there's 1 missing. That's right. That's fine. That's fine. That's fine. Right, we're going to go over to lovely Eleni, who's been waiting patiently in the green room. She got 1 answer right or 1 answer wrong. So she's a force to be reckoned with in round 2. Hi, Eleni.
Hi, everyone.
Hey, how are you?
I was only just playing around. People don't have to worry. I'm not going to participate. I realize it's not for the employees. So,
how are you, my head-standing, wonderful yoga superstar, supernova?
Oh, that's quite a big title. I'm okay. Thank you very much. Holidays are almost over. Term is starting soon, so I'll be back in the classroom, and I'm not super excited about it, but well. Could be worse.
Oh dear me! And look at us, we're both wearing warm clothes as well.
Yeah, it's chilly. It's quite chilly, isn't it?
Not just my imagination, then.
No, it's not summer anymore. That's sure. Hi, Ian.
Oh, that's so sweet. Kath says hello.
Hi, Kath.
Jed says hello.
Nice. People are so nice. Hi, Jed.
Oh, it's so nice. It's so lovely, isn't it? Hi, Vicky. Just found. I'm sorry, Bob. We're now on Tuesdays for the foreseeable. It just means the reason why we're doing a pub quiz, Eleni, is because on Thursday nights, our brilliant pub quiz starts up at our local pub again. And it's the only night where I'm surrounded by a group of people. Otherwise, the rest of the time, I'm just on my own. So I need human contact. So it's wonderful that you and Sonia can join me on a Tuesday. Thank you so much.
You're welcome. I love the show. So whenever I don't have too much studying or too much work to do, I'll be here.
Wonderful, wonderful. Okay, Eleni, well, I'll let you proceed at light speed with your amazing presentation.
Perfect. Before we say anything about the presentation, I wanted to say I got myself a lamp. It's a moon.
Oh, hang on a minute. Let's make you full screen there.
Moon. It's so cute.
Let's have a look. Oh, Crumbs got rid of her. Hang on a minute. We need to see this. We need to see it in full because they are so good. Where's the full screen button? Hang on. Oh, solo layout.
I was really excited by it. Like, and I can change it's got a little remote and I can change the color so I can get like a white bluish thing. And I can get like a light gold, and then I can get like a deep gold, and then I can change the intensity as well. And I thought, because we were talking about getting a lamp so I don't appear dark on the on the presentations, and I was like, I think a moon would be appropriate. So I think that's quite it should brighten me up significantly, or I hope it does.
Well, I've got something lovely to tell you about those moon lamps. They make an absolutely extraordinary photographic prop, and I just want to show you.
Okay.
I took some pictures of a little girlfriend with one. When was it? I'm just scrolling back. It was only the other night. Honestly, if you put those in photographs, it looks insanely beautiful. I don't know whether you can see that there.
Oh, wow. Oh, yes, that's good.
Yeah.
That's really good.
And you can get really arty with them. And you can do amazing stuff like that.
Oh, wow. Okay. I hadn't even thought of these things. My artistic brain is completely absent.
Yeah, they just look so good in photographs if you take some decent pictures of it. Yeah, it's a beautiful object. A beautiful object.
I'm glad I got it then. I'm really glad I got it. Hopefully it's gonna keep me nice and bright for the presentation. So
okay, Eleni. I tell you what I have got, which is really good. A little ring light there. That was about £5 off Amazon, and it just goes on the tip of my computer as well. So that's a handy one.
Okay, that's handy. I'll try that as well.
Right, cool. We'll get you on the presentation. I'm going to disappear and just assume that all is well.
Perfect. All right. So I'm going to make this into a slideshow. And is everything looking okay? I hope it does. So it's been a while, and I didn't know I had so many emails in my inbox, and I was trying to choose what to present tonight. And so it happened that both of the items I'm presenting are actually observed by the same instrument, which is quite an interesting coincidence, and almost a week apart, which is also another interesting coincidence. But yeah, I thought I would start with the fastest orbiting asteroid discovered in our solar neighborhood. And this picture is, of course, an illustration, and it shows the said asteroid, which is officially named 2021 PH27. And this is Mercury, and this is the Sun. Now, this asteroid was actually observed with the dark energy camera, which is mounted on the Victor Blanco 4-meter telescope in Chile, which is part of the, let's see, CT, I think that's like, I can't remember this acronym there, which is the larger bit where the Victor Blanco belongs to. It's a something observatory, but my brain right now has switched off about that acronym there. So this is the asteroid, or the illustration of the asteroid, and it's particularly interesting because it's actually the fastest orbiting asteroid in the neighborhood, putting it at a closest point from the Sun at about 20 million kilometers, which is a lot. And it at its closest point, it basically grazes a little bit of Mercury's orbit as well, and it actually crosses both Mercury's and Venus's orbits. And it's particularly interesting to know that there are objects that are actually closer to the Sun, especially objects like asteroids, than previously thought. And it is actually the object that is more severely affected by general relativistic effects, because it's so close to such a massive object, aka the Sun. And the other little interesting bit about it is that the asteroid's inclination suggests that it was actually an extinct comet that happened to pass too close to the terrestrial planets at some point in its orbit in the past, and it was captured by one of them, making it the closest asteroid to the Sun. And I thought that was pretty cool, that we're still kind of discovering things in our solar neighborhood that, it's a place where you think you know everything, but you actually don't. We still find new things all the time, and I thought that was a pretty cool thing to share with you. And now we're going to go from an asteroid to a spectacular portrait of Centaurus A. It is indeed spectacular. It's got a very strange shape, which I will explain where it comes from. And before we do that bit, we will do the introduction. So Centaurus A is a giant galaxy, and it can be seen in the southern hemisphere, in the southern hemisphere sky. And it's in the constellation of the Centaur, or Centaurus. And this particular galaxy is probably, most likely, the result of a galactic collision between a giant elliptical galaxy and a smaller spiral galaxy. And this is why it's got this incredible amount of dust in front of it, which is obscuring the center almost completely. But it's not without its advantages, if you want. So for starters, it makes for spectacular tendril-like structures that look good in this picture. And secondly, it gives the galaxy a widespread star formation. And the star formation is evident both by the red, you can't actually see when I move my cursor, I need to remember that. So the star formation is evident both by the red hydrogen clouds, which can be seen at the bottom left and top right of the dust lane, and also by the blue faint stars that you can see at the edges, at the top and the bottom of the lane. That's the best I can do. I am not sure why people cannot see it when I move my mouse, but hopefully that could give you an indication. Now, this galaxy is actually one of the most well-studied or exhaustively studied giant galaxies in astronomy history, if you want. And since its discovery, which was in 1827, it has been observed by all sorts of telescopes. And there is different observations in radio, in X-ray, in all different wavelengths. And it's been used a lot as a probe to understand giant galaxy formation and evolution. So it's been a well-studied object, and it also makes a great target for amateur astronomers who find themselves in the southern hemisphere, because you can actually see the dust lane and the bulge just by using binoculars. So if you ever find yourself in the southern hemisphere, that's something you can look for in the night sky. And now we're going to go to Aurora Alert. Okay, it's been a while, and before the last time we had Pop Astro show that was there had been like 2 presentations, maybe 3, that did not have any auroras, any upcoming auroras, and I feel like I disappointed people. So good news, we are having a strong aurora alert, as there are 2 different kinds of events, 2 different CMEs heading our way, one from a solar flare and one from a magnetic filament eruption. So hopefully we will be able to see some spectacular auroras in September 1st or 2nd, which that will make it tomorrow and Thursday. Tomorrow and Thursday. So hopefully we will get some auroras in. If not, my apologies, I'm only the messenger. I bring it up with the sun and its solar flares. Now, last but not least, astronomy picture of the day. Hopefully you should all recognize this, I hope. It's the moon, but the moon as never seen before, if you want. So in this picture, let's just say that before we start with this picture, usually when you look at the moon, you don't see these colors. You usually see either a silver gray moon or a gold, maybe with a bit of orange kind of moon. But what's happening here is that there's always some small but measurable color differences, and they have been greatly exaggerated for the purposes of this picture. So the color differences are real, but here they're just being brought up a lot for the purposes of the image. And each color variation corresponds to a different chemical profile in the region of the moon that you're looking at. So the bluer regions are titanium-rich regions, and then the ones that are a bit more orangey, yellowy, or white, they are regions that are poor in titanium and iron. And that goes to show that by combining what we already know, like visual, measurable color differences, with what we know from sampling and analyzing the chemical profile of the moon, we can produce pictures that can be highly informative. And I think things like that can be used in schools because they're easily understood and easily analyzed. You don't have equations, you don't have anything fancy, you just have different colors, and from there you can start a whole conversation about what the moon is made of and so on and so forth. That was my little bit of astronomy outreach there for anyone interested. So I will wrap up with that, and I think it's a very beautiful picture. It makes for a great poster even. And I will pass it on to Vicky.
Oh, Eleni, thank you. I'm sorry about Cosmo. He gets very excitable.
That's all right. That's okay. He's one interested sloth. Maybe you know, if more people were like this sloth, we would be a little bit more educated in astronomy than we currently are. So kudos to Cosmo.
Oh, Eleni, guess what we forgot?
I think we do it all the time. I think let's just accept that my song will be played afterwards.
Okay, you know? Right. Okay,
I'm
here we go.
Here she is with the space news. It's Eleni, it's Eleni. Prepare to be astonished by Eleni, by Eleni. When she's not reading Tolkien or teaching a class, she's doing yoga and toning up a PowerPoint presentation for astronomer emulation.
Oh, and
I think it closes the presentation quite nicely.
There you go. All right. Well, I'll stop referring it to as a botch mistake and just as a beautiful tag for you. I've made a song for Steve Tonkin as well. Have you ever met Steve? Steve, I'm coming to you. In 3, 2, 1. Steve Tonkin.
Hi, Steve.
Hello, Victoria. Hi, Eleni. Yeah.
Hi.
No, I'm here in trepidation. There was a sort of preview of this first few bars on LinkedIn, and I think I'm sort of I'm in for embarrassment, I think.
Oh, it's a lovely song. So Jed Mac Eleni says,
oh, thank you, Jed.
Thanks, Eleni. They love you, Eleni. What more can I say? You truly do get astronomer adulation. Steve, you want to hear your song?
No.
It will be great, I'm sure.
But I don't have a choice, do I?
No, I took at least 90 minutes to make this, Steve. Right, it's coming in. 3, 2, 1. You get it twice. You get it once at the start and once at the end. So it's a 2 for 1, my love. Okay, here it comes.
Steve Tonkin, the binocular astronomer. He believes that 2 eyes are better than 1, yeah. And he's a dark sky warrior.
And did you know that Steve is actually short for Stonkin?
For a tour round the heavens high, try his book, The Binocular Sky. You won't believe either of your eyes, Steve Tonkin. Oh yeah.
I can't believe either of my eyes, the left nor the right. What a view.
Good.
I'm not sure I deserve praise like that, but hey.
I think you do, Steve. You're nearly one of my favourite astronomers, so what more can I say?
Well, okay, nearly. Okay, right. The nearly man.
The nearly man. Well, I
no.
don't have a favourite astronomer, but you're definitely right up there in the top echelon.
Thank you, Vicky.
Very good. We'll play that again at the end. Eleni, goodbye and see you next week.
Bye, everyone.
Nice to meet you, Eleni. Bye.
Nice to meet you too. Bye.
Hey, Steve. Good evening. Thank you for agreeing to come on the show. It's really nice of you to come on at short notice.
That's okay. You know, I'm a sort of media slut. I'll do anything.
Yeah, well, that's why. It's because the show's moved and it just caught me by surprise. It was like, oh wow, I don't know whether I've got a guest. Steve Tonkin, and you've come up for me. So thank you so much, Steve.
That's a pleasure.
Yeah, I know you love broadcasting. Your hair's looking rather godlike.
Oh, I cut it.
It's nice. Send
Too
some
short
my
to
way.
tie back properly now, so never mind.
Oh, it matches Cosmo.
Well, same colour, yeah.
What? No, he's not your dad. He's not your dad.
No, I know he's not. Oh, you're talking to Cosmo, right?
Yeah, I was talking to you. Yeah, talking to Cosmo. Right, Steve, what's your presentation on this evening?
Talk about fuzzy blobs. Fuzzy blobs, faint fuzzies, these fuzzy patches we see in the sky. And, when you start out in astronomy, yeah, you're just sort of going for them. You're looking at them. You're trying to, or at least I was, seeing how faint you can get and all the rest of it. But actually, they teach us a heck of a lot. In fact, they probably teach us more about just about anything other than spectroscopy about what's going on in the night sky. So I just thought, well, hey, let's do this fuzzy blob guide for the perplexed thing, which I actually put it together part of a course I was teaching. When you realize that your students are saying, what's the difference between a planetary nebula and an emission nebula and a reflection nebula and all the rest of it, and why do they have these names? So I thought, well, let's do something and sort of pull it together and take it from there.
Super smart. So are you going to do a presentation? Are you doing a slideshow, Steve?
I am indeed. So
that's
let's
good.
Just kick that off. Right. Share screen. Yeah, it doesn't tell me which one I can share.
Welcome to the awkward screen share minute.
Right.
Look at that. He's done it. Oh, I see pretties.
Yay. So here we go.
Okay, I'm going to remove myself from the feed just for a minute.
And I should probably remove myself as well. But hey, never mind, because it's the sky that speaks for itself. So here we go. Fuzzy blobs, a guide for the perplexed. Need to move this on. Just hang on a mo, folks, because as in normal Tonkin manner, I have managed to get my on pointer. And back onto StreamYard. Sorry, everybody. I'm not used to using StreamYard. So here we go. So fuzzy blobs, what's it all about? Well, here we've got a bit, you can actually see this in the sky at the moment, if the clouds ever clear. Down in the south, this is sometimes called the Rho-Ophiuchi complex. And what we've got is a lot of fuzzy stuff, essentially. It's fairly obvious that it's fuzzy stuff because, quite frankly, it's, without putting too fine a point on it, it's fuzzy. So what are fuzzy blobs? Well, essentially, we're talking about nebulae. Nebulae, galaxies and clusters. Nebulae is the sort of generic name for various cloudy patches in the sky. They're predominantly interstellar hydrogen, helium, ionized gases, and dust. I mean, the dust is pretty obvious in this one, isn't it? It's sort of fairly dark there. And they get all these colors with them as well, which is very nice. And most of what we can see are what are called diffuse nebulae. And most nebulae fall into this category. They're sort of extended regions of gas, dust, no well-defined boundaries. Many of them are star-forming regions, or stellar nurseries, we call them. And they include emission nebulae, which are shown here in red, reflection nebulae, which strictly speaking are shown here in yellow, but also the blue counts as that as well. Planetary nebulae, we haven't got any in here. Supernova remnants, dark nebulae. If you want to know, well, you see a bit here, but if you want to know about dark nebulae, please do read Martin Griffiths' excellent article in the current Popular Astronomy. It really is one of the better articles on dark nebulae that I've seen. So moving on, here we've got absolute brilliant red. This is your classic emission nebula. This is, I don't have to read it for you, do I? But it's IC 1396. It's about 2,000 light years away. And what we've got here is regions of ionized gas. Yes, of course, there's dust in here. that emit light at various wavelengths, but it's predominantly, and that's why I've chosen this one, it's predominantly red. And this is called hydrogen alpha radiation. And it's you see it in colored photographic images. You won't see the red in a visual image. There's just not enough of it to trigger your codes. But if you take a timed exposure, you can pick it up on the chip of a camera. The gases, the gas molecules, they're excited by what's usually a nearby very hot, in other words, blue star. And so this is the sort of thing we'll talk about. This is a sort of a representation of what happens inside an atom. And your electrons around the nucleus can have various energy levels. So their lowest energy, they're down at 1 here. But they can be in a number of other places. In fact, electrons can be an infinite distance away, which is possibly what you get when you ionize a gas. Well, it won't be entirely infinite, but it could be according to quantum theory. And when you put energy into the gas, it forces an electron to go to higher and higher energy levels. And then when you take that, whatever it is, radiation that's forced to get there, you take it away, it falls back. And when it falls back, it emits a very, very specific wavelength of light. And the one we're interested here is this second lot, the Palomar lines, because these are in the visual part of the spectrum. Lyman are too much in the ultraviolet, all the rest are in the infrared. There's others going on beyond this as well, like the Humphreys, which comes down at 6 and so on. But we're really just interested in the Palomar line spectrums. So this is what's happening. With your Palomar series, as it's sometimes called, Palomar alpha is when it falls down 1 energy level to the second energy level here. Beta is when it falls down 2 energy levels, gamma 3, and so on. And when it does this, it emits a photon of light. So each time it emits a photon of light. So this is your hydrogen alpha here. The hydrogen beta, because it's fallen further, emits more energy, which means more blue, more to the blue end of the spectrum. With light, the more towards or beyond the violet end of the spectrum it is, the more energy. The more red or beyond the red end of the spectrum, the less energy, and so on. So we've got hydrogen alpha, hydrogen beta, hydrogen gamma, hydrogen delta, hydrogen epsilon, and so on. And these are the emission lines that you get. So when it falls back, it emits this. We have also absorption lines. So if you shine light on a cooler gas and it absorbs the electrons, absorbs the energy to push the electron out the other way, you get a dark line in there. And this is important because we're going to come back to this later, because this is what we're looking at often with redshifted light. But we'll come back to that later and see what's going on there. So let's just take Orion's belt, which you can see it now. It's about 3 o'clock in the morning. Get up there, you'll see it. And down below the belt, we've got this little patch down here, which is the Orion Nebula. This is an image taken with a 200mm lens on an ordinary DSLR camera. This I took before the days of CCD chips. Well, it wasn't quite before the days of CCD chips, but I took this on film anyway. Okay. So this is what you might pick up with just an ordinary, very, very simple setup that you might have at home. If you happen to have an Anglo-Australian telescope like David Mallon did, you might pick up something like this, and it looks a bit more interesting. And it's not completely flippant to say that if you have a Hubble Space Telescope, you'll get this. And I say it's not flippant because anything that the Hubble Space Telescope produces is available for you to download the raw data and process those data as you see fit. So you do actually have access to a Hubble Space Telescope. Now, if we go even deeper into this nebulosity here, what we get, you see what we're getting here? We're getting these structures here. And if we look at those structures in more detail, which the Hubble Space Telescope can, and you can with Hubble Space Telescope data, what we've got is stars forming. Here's a star here. These things are called proplyds, protoplanetary disks. And we've got round the outside here a possible disk of planets about to form around the star. Here we're looking at one obliquely. And we've got these emission nebulae all over the sky. Well, not strictly speaking all over, but in lots of places in the sky. It's one my good friend Pete Williamson took. This is the Rosette Nebula in Monoceros. And we've got these structures here. You see these very little dark structures around here. And they're called Bok globules. And they're little regions of dust and gas. And they may well contract ultimately to form stars as well. With emission nebulae, which are essentially our star-forming regions most of the time, associated with them, we have what are called reflection nebulae. And you know, the thing you notice here is an immediate color difference. Strictly speaking, they're not reflecting light, they're scattering light, but we'll see why that is sort of important later. But just remember the yellow nebulosity you saw in the first image. And you've very obviously got dust around in this as well, haven't you? You know, you can see that there's stuff there. So all of this stuff is not stuff that formed the Big Bang. All of this stuff is stuff that formed in stars. It's stuff that's already been through at least one star. So what's going on to create the blue? Well, it's essentially the same thing as that creates a blue sky. It's called scattering. And with oxygen molecule, nitrogen molecule size things in the atmosphere, you get what is called Rayleigh scattering. And Rayleigh scattering, see, we've got the direction of incident light here, but Rayleigh scattering happens in all directions, predominantly forward scatter and back scatter. But the important thing about Rayleigh scattering is it's dependent on the wavelength of light. And the shorter the wavelength, so the more to the blue end of the spectrum you get, the more it's likely to be scattered. The more to the red end of the spectrum you get, the less likely it is to be scattered. And we see this in our own sky. The sky looks blue because the blue light is scattered. The sunset looks red, or if you look at the a lunar eclipse, the moon looks red because the light that's going through it is light that hasn't been scattered by the atmosphere, the red end of the spectrum. But we've also got this phenomenon called Mie scattering. I've probably pronounced Mie incorrectly, but please somebody correct me at some stage if I am. And Mie scattering is sort of things you get from dust particles and such like that. And you can see that this is predominantly scattered in the direction of the incident light. And the larger the particles, the more it is there. And so what you're getting there is something that is going to be producing the color of mostly the color of the light that is being scattered. And the reason for that is that Mie scattering is not so wavelength dependent as Rayleigh scattering. And you can see this very, very easily for yourself if the clouds clear in a nice summer sky. So if you're looking away from the sun, the sky looks a nice deep blue. The sky looks nice deep blue because you're getting mostly Rayleigh scattering. The more and more you look towards the sun, the more you get this whiter glow around it. Sunlight is essentially white, and that is because it's being dominated by Mie scattering. But when you're looking very far away from the sun, 90 degrees away from the sun, you're hardly getting any Mie scattered light. You're getting almost all Rayleigh scattering, so that is dominant. So what we can see going on in our atmosphere is also exactly the same processes that are going on in deep space when we look at these things. So we see something like the Flame Nebula and the Horsehead Nebula. This is the left-hand star of Orion's belt here. Here's the Horsehead. You see, we've definitely got Emission Nebula here. We've got a bit of dust here, and certainly the blue here. So that tells us that is reflection nebulae or scattered light. And then around here with the flame, we've got yellow light, and this is true reflection. So it's a mixture of Mie scattering and true reflected light. So the light from the star is actually being reflected off the particles here, and that is why it's that color. If we go back to the first image I showed you, let's just do that quickly. Boom, 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 boom. So around here, this is the star Antares, which is slightly red. And you can see this, the light scattered from that is certainly towards the red end of the spectrum. I should also mention, actually, if you want to know which one Rho Ophiuchi is, you can just make it out here. This is Rho Ophiuchi. It's the one I always think it looks like Mickey Mouse. It's you might just be able to pick that up here. It's got one bright star, and here at about 12 o'clock and 4 o'clock from it, you've got two little fainter stars that make it look like Mickey Mouse's ears. And this structure here is actually a globular cluster. We'll come on to clusters later. That's Messier 4. Let's just move back on through these, go back to where we were. Right, so that's the flame and the horse head, which again, you'll be able to have a good look at this autumn and, well, late autumn and then through the winter. You have to be up quite late in autumn to see that. Okay, then at the other end of a star's life, we have these things called planetary nebulae, and these are, in astronomical terms, they're incredibly short-lived. They might last a few tens of thousands of years, and that's it. And they're just masses of plasma that result from the death of stars. And they've got absolutely nothing to do with planets at all, but they get their name from the fact, and you can see it in some of these images, that in early telescopes, they had the appearance of these sort of ghostly planets. So they were nebula, they were cloudy, they were these diffuse objects, but they were round about the shape of planets. So they were just called planetary nebulae. Nobody had a clue what they were. When they started doing spectroscopy on these, now you probably know that helium was first discovered on the sun. People doing spectroscopy on the sun found lines, spectral lines in there that in the sun spectrum that they couldn't produce with anything on Earth. So they named it after the sun god Helios, which is why it's called helium. And later it was discovered on Earth. In some nebulae, you get another set of lines which they hadn't found on Earth there. And in the late 19th century, a man called William Huggins, he thought he'd discovered a new substance as well, which he called nebulium, because it had been found in nebulae. It actually turns out that it's a particular transition series that you get with oxygen. It's called forbidden lines. It doesn't actually happen easily in the sort of circumstances we have on the surface of the Earth. But that is, so nebulium, if you ever hear about it, it's actually oxygen, oxygen 3. You may well have an oxygen 3 filter, I've heard of them, which are very, very useful for looking at planetary nebulae, really for that purpose. And what we get with these, what we can see here is you've got the progenitor star, or what's left of it. So these are sort of things around solar mass stars, and it's chucked off its outer atmosphere and the core is now dying. You've got the same thing here. If you're looking, this is the Dumbbell Nebula. I think it looks much more like an apple core, so I always call it the apple core nebula, but what you call it's up to you, really. Other people call it the Diabolo. This is the Ring Nebula, for reasons that are probably obvious. If you looked at this from the side, you'd get this. If you looked at this from the end, you'd get this. Due to the rotation and the magnetic fields and everything else that's going on there, the material that's thrown off is thrown off in sort of cones in two different directions. Very often, what's going on when stars emit stuff is they go off from basically the spin poles or the magnetic poles of the star. Okay, moving on. If you have a bigger star, you don't just get this sort of nice little poof into 10,000 years of planetary nebula. You get cataclysmic destruction. This is catastrophic. So in core collapse supernova, this is the supernova from 1054, SN 1054, otherwise known as the Crab Nebula. This is the one where Jocelyn Bell Burnell discovered the pulsar and started to figure out what was going on, and so on and so forth. Didn't get a Nobel Prize for it. Her supervisor did. She's says she's never been bitter about that, because if she got a Nobel Prize then, she'd never got anything else. And as you can see around, well, she's got a heck of a lot of other stuff since, which she does really good work with as well, and donates her prize money to people who need it. That's great. So this is the Crab Nebula. This was catastrophic, and this is changing still. So if you look at Hubble Space Telescope images, and even now with modern good modern amateur kit, you can do this. You'll see that over a period of a decade or so, the structure of this changes very slightly. Now, the other thing that's chucked up, that these things give out, apart from the optical, which you can see they give a lot of X-ray emissions, come from ionized gases. They give radio emissions, and that's due to something called synchrotron emission. What you get is you get electrons being accelerated radially as they spin down magnetic field lines. Okay, but of course the other stuff that gets chucked out by stars when they explode, apart from the gases, is the stuff that's been made, a lot of which is carbon. And again, I've already mentioned Martin Griffiths' excellent article on dark nebulae in this month's Popular Astronomy, and here's an example. This is an example. This is the Snake Nebula. And what we're looking at is gas and dust, well, in this case, mostly dust, that has been made in stars and has been chucked out in one of these processes at the end of a star's life. Initially, when people looked at these things, they thought there were gaps in the Milky Way. And they're not. It's not gaps, it's foreground dust. This one here, which will almost certainly turn out to be a Bok globule, is one that demonstrates this. This is sometimes called B68. You'll find a lot of these have B numbers. That's for Barnard. E. Barnard was the astronomer who did a lot of work on dark nebulae about a century or so ago. But they do look like these voids in the sky. And let's have another look at that one, slightly closer. That's what it looks like in visible light. But if you look at that, so there's nothing in the middle, is there? But if you look at that in infrared light, it suddenly changes. So it's, again, red light is more easily transmitted, so infrared light is more easily transmitted than visible red light. So in infrared, you can see that this is hiding a lot of background stars. Let's look at the visible light one again, and then we look at the infrared. And this is probably a Bok globule. This is something that could very well collapse and start forming a new star and solar system. It might not. It might. You know, all these things are vaguely probabilistic. But this is a good time of year. If you want to have a look for dark nebulae, the region down from Altair and south is very, very good for this. So this is the star Altair here, and it's got like its two outriders. And even in binoculars, you can pick this up. This is Barnard's E, or it's an underlined C, depending on what you see there. So this is a nice bit of dark nebulosity. It's a very, very easy one to pick up. 10 by 50 binoculars. You do need a dark sky, though. Dark nebulae disappear very easily. In the southern hemisphere, some of them are much more prominent, and in certain southern hemisphere cultures, it's the dark nebulae which have mythological significance. So it's the great emu in the sky in Aboriginal Australian culture, and so on and so forth. And some South American cultures, there are whole mythologies built around these dark nebulae. But let's summarize what we've got. So from a molecular cloud, which is stuff that's already been through a star, it condenses. It can either form a sun-like star over here. It's yellow, you know, the sun's a yellow dwarf star, isn't it? End of its life, it becomes a red giant, explodes into a planetary nebula, chucking off its gas and dust. The progenitor star becomes a white dwarf, which eventually cools down and dies. And the material that's thrown off becomes part of the interstellar medium, where it can be recycled again. Or if there's more of it, and you get something at least 3 times the mass of the sun, whole thing is driven by gravity, there's more of it, so everything's going to happen much quicker, it gets a lot hotter. So this is your a blue-white star. Again, the end of its life, it may expand, become a red giant, and then you get this cataclysmic explosion at the end, which could go either of two ways. So you could either get your supernova remnant with a pulsar, or you could get a black hole. About 8 solar masses is going to give you a black hole. And all this is stuff that can really just be learned just by looking at fuzzy blobs and analyzing what you see. There was another kind of fuzzy blob that, if we're going back a century and a half, that they weren't quite sure what was, and that's what they call the spiral nebulae. So these are sketches that were made at the time. With modern photography, we know what these are. These are what we call the galaxies, same word that we get Milky Way from, as a galactos. And just over 100 years ago, there was a big debate. Are these part of the Milky Way? Are they our local environment? Or are they something that's much, much further away, sort of so-called distant island universes? Well, we're looking at this. Have a look at the red. This is all emission nebulae you're seeing around here. This is Bode's Nebula, M31. Very nice. Again, you can see it easily in binoculars or anything like that. At the moment, it's well placed in the sky at the moment. If you take a diagonal across the bowl of the Big Dipper, the plow, the saucepan, whatever you want to call it, and just the same distance further on, this is where this and another galaxy, M82, Cigar Galaxy, are here. But we see we've got, even these other galaxies, we've got these emission nebulae, these red star-forming regions. So how do we find out how far away they were? Well, this was due to somebody called Henrietta Leavitt, who we'll have a look at the moment. And what she was doing, she was analyzing a particular kind of star called a Cepheid variable. Delta Cephei is one of those. It's not actually the first one that was discovered, but it's the one for which they're named. And they are variable stars. That means stars that vary in brightness, and they do so in a characteristic way, which is quite a steep increase in brightness. They're not such a steep decline in brightness, and they are regular as clockwork, just about. But what Henrietta Leavitt, here she is, discovered, was that the period over which they oscillate in brightness is very, very closely related. It's a linear relationship here to their luminosity. And the way she did this was she looked at the ones in the Magellanic Clouds. Now, okay, they're not all exactly the same distance away, but it's like sort of, you know, if you're sitting from where we are, you know, we could imagine that all the street lights in, say, New York are effectively the same distance. So it's the same. It's effectively the same thing. And she worked this out. And from that, you can, as long as you can measure the period of the star, you can tell how bright it is. If you know how bright it is and you know how bright it looks, you can tell how far away it is. So something called a standard candle. So, or it's a standard, or at least standardizable candle. And this is what Henrietta Leavitt did with these Cepheid variables. And then by looking at these things in distant galaxies, for example, the Andromeda Galaxy, figure out, well, actually, this thing's not part of us. You know, this thing is, you know, a couple of million light years away. So, you know, you're beginning now to get an idea from what you're able to do with these, what's going on in these fuzzy blobs. In this case, of the fuzzy blob, which is one of the Magellanic Clouds, you can start to see what's going on there. Now, I said right at the beginning, look at the absorption lines, because this is what to do with redshift. Redshift happens when an object is moving away from us. It's just like the Doppler effect you get with sound. It's analogous to that. So as a small boy doing a car coming close and going away, as it's coming towards you, pitch is higher. As it's going away from you, the pitch is lower. And so with light, longer wavelength, you're moving more to the red. The thing is, how do you know what wavelength it started out as? And the way you could do that is by looking at these absorption lines. So this is where they are in something that is stationary relative to the observer. If the thing is moving away, all these lines shift to the redwood. For things very, very, this emission lines right up here, you can get things in the ultraviolet which are shifted into the visible. And you get exactly the reverse happening when something's coming towards us. The Andromeda Galaxy, for example, is blue shifted. So this means all the lights will be shifted the other way. So it's where you pick up these patterns of lines. And by doing this, Edwin Hubble was the person who gets all the credit for it. Here he is. He plotted recession velocity from redshift against distance, which he could get from Cepheids, and we'll see a little bit later how you can get it from globular clusters. And he came up with, well, it's not a perfect relationship, but it looks sort of, there is certainly a general trend that the further away something is, the greater its recession velocity. So again, now we start to get this idea of an expanding universe. Up until then, people had thought the universe was stationary. Certainly Aristotle thought so, Newton thought so, and of course Einstein thought so, because that's why he introduced his fiddle factor, or what we call nowadays the cosmological constant, into his equations, which actually made the universe stand still, which is what he thought was going on. But the person who did the real work was a bloke who started off as a caretaker and all that, and he was a meticulous observer, and he doesn't get the credit he deserves, and that is Milton Humason. And Milton Humason did a lot more work on this. You see, here's Hubble's 1929 data. You can see here, 2 years later, Humason had done much more, and this idea now that recession, velocity, and distance are related in general. I mean, it's certainly with galaxy clusters. Within a galaxy cluster, no, gravity still plays a part. But galaxy clusters, that we've got this idea now that recession and distance, recession velocity and distance are there. It ties down this idea of an expanding universe. So that's what these guys did with redshift, and showing that the universe expands. And of course, the thing we get from this now, if we can measure the speed of recession, we can know how far away something is. And this is really quite important, because our standard candles are only useful up to a certain distance. They at something like 500 megaparsecs or something like that. You can't use things like globulars and Cepheid variables. So this is how we measure the size of the universe. And what is often done is particular types of supernova, you look at where the spectral lines are in that, and you can tell how far away they go, and you start getting things happening. Actually, it's not only that the universe is expanding, but actually the expansion seems to be accelerating and so on. But that's a completely different talk. Moving on. Clusters, which we haven't really talked too much about yet. You've got to start somewhere, and so all these things go in sort of cycles and whatever. So where we start, it doesn't really make any difference. So clusters are gravitationally bound groups of stars, from anything from a few dozen to a few 100,000 in number. And there's two types really: there's globular clusters and open clusters. Here's a globular cluster. This is Messier 13. You can go out and have a look at this tonight if the sky clears. This is in Hercules. So if you take the keystone asterism in the middle of Hercules, a third of the way from the top right-hand star to the bottom right-hand star, as you're looking at that, or as it's lying now, possibly the bottom right-hand star, bottom left-hand star might be more accurate. A third of the way down, you'll find that. Again, very, very easy to see. You could pick that up in 30 mil binoculars on a decent night. So these are very tightly bound. So that's why they're approximately spherical. So there's a lot of gravity going on there. So they're clusters of tens, hundreds, thousands of stars, and they tend to orbit in a halo around almost all large galaxies that have been observed. And you know, sort of 30 years ago, even 10 years ago, you know, people, they formed at the same time as the galaxy. Now there's increasing evidence that actually these might have been very, very small galaxies, satellite galaxies that have had their spiral arms, or whatever they had at the time, their outer stars cannibalized by the gravity of the host galaxy. So it's a lovely thing about astronomy and astrophysics, and that is, you know, there's always these mysteries. You never quite come to the end of it, and we keep trying learning more. But we can observe these around other galaxies as well. So this is the Andromeda Galaxy here. Again, that's well up in the sky now. So if you've got a reasonably good northeastern sky, you can go and have a look at that as well. But this here, called MAL 2 or M31 G1, M31 Globular Cluster 1. That's Palomar Observatory Sky Survey. If said, you know, you use your Hubble Space Telescope, and here it is, definitely a globular cluster. In the same image from Hubble Space Telescope, we had this one, same image put out by the same slide, so not the same image. And this is M15, which is one we have on in our own galaxy. But you can see now that we've definitely got these things in other galaxies, and the assumption with this is that, well, assuming galaxies all formed in the same way, which there's no reason to assume they didn't, and lots of very good reasons to assume they did, then what's going to happen is that your globular clusters are going to form in the same way. So the brightest ones in one galaxy are going to be approximately the same brightest as the brightest ones in another galaxy. And again, you're to the thing, if you know how bright something is, you know how bright something looks, you can tell how far away it is. You never ever use one of these distance measures, only one of them. You use 2 or 3 or more, and you know, make sure you're getting consistent results from all of them. So that's your globs. The other kind is open clusters, and these are associated with the star forming regions. So this is the Heart Nebula. IC 1805 is actually the cluster in the middle of it. And because it's got a bit of nebulosity next to it, you know, it's got to be called something, hasn't it? You've got something that looks vaguely cardioid here. So they called it, well, Heart and Soul. I better not sing, really. So this is called the Soul Nebulae. But what we've got here, we can see it, the cluster stars are these bright blue, these hot new stars. And these, again, coming up in the morning sky, you can have a look for this. This is the Pleiades. And you can see we've got these very, very hot blue-white stars, and they are associated with a lot of reflection nebulae or scatter here. This isn't the stuff out of which they form, by the way. They are moving through space, and this is a region of gas and dust they're moving through, and that is why we are getting these lovely nebulosity effects. And the first time I saw an image something like this, I thought, oh, somebody's painted that and left the brush strokes on. But no, I was completely wrong. But you can see from around it that what we're seeing really is the dust and that's around it. So this is the Pleiades, and this is a typical open cluster. This one's relatively nearby, so only 17.5 light years here. And you know, sort of a few dozen stars, well, more than a few dozen. It depends on what you've got, how many you can count, but there's certainly more than the so-called 7 sisters. And mostly very, very blue, hot blue stars here. The red stars, the yellower stars here, are probably not cluster members. Okay. And these are all over the sky. We'll go back to one that we looked at a little bit earlier. So this is Orion's belt. And of course, everyone just looks at Orion's belt and says, ah, yes, we go down to the nebula over here. Don't do that. Look around here. This is an open cluster. This is Colander 70. It is absolutely stunningly beautiful. And a telescope won't show you any as much as you want to see at all, because you can't see all of it. 10 by 50 binoculars, 15 by 70 going for it. And it is stunning. There is so much going on here in this huge OB association of stars. O and B are hot stars. So you've got this S-shaped curve going through here. So well, you can, when you look at that now, for every time you see it, you can think, oh, S, yeah, that's for Steve who told me about that, and ruin your evening's observation. But if you prefer, well, that's the head and the neck of a swan, and here's its wing up here as it's sailing through. Well, it's pareidolia, but if you can't enjoy these things and find your own pictures out of them, and then NGC 1981 and NGC 1975 down here before we get to M42, which will eventually look like one of these once the star forming is finished. Now, it doesn't end there, because these things are not evenly distributed in the sky. So if we take something, and I'm using 1st of August at 2200, 10 o'clock, because this shows it, I think, quite clearly. The orange are your open clusters, the things we've just been looking at. And they fall along, I haven't mapped the Milky Way onto this, perhaps I should do, but the Milky Way also forms this arch across the sky here. So where your Milky Way is, which is actually the spiral arms of our galaxies, we'll see in a moment, that is where the open clusters are. These are the star-forming regions. These are the ones that we saw in the image of the galaxy M81 that I showed earlier. Your greens here are your planetary nebulae, and they're generally closer to the arms of the Milky Way, but that's mostly because there's more stars there. So you expect there's more stars, there's going to be more dying stars there. As we look out away from there, we can see the red things. These are our galaxies, which aren't obscured by the gas and dust of the Milky Way. And neither, as we look away from the Milky Way, are the black bits here, which are the globular clusters. But notice the globular clusters are mostly in one direction. They're towards the south. At this level of depth that we're going to for this chart here, we don't see any globular clusters to the north. And using this distribution, Harlow-Shapley figured out where we are in our galaxy and approximately what our galaxy looks like. So we've left that there. We are round about here, about 2/3 of the way out, between half and 2/3 of the way. When we look south, we're looking this way. We're looking towards the bulge of the galaxy. When we are looking out of the galaxy here, this is where we see the other galaxies up here and down here. And notice, because of where we are, the globular clusters are clustered, for want of a better term, primarily to the south of us and not to the north, which is exactly what we're seeing here. So doing this and just looking at where these things are, people, and you could as well, work out where we are in relation to the rest of our galaxy. And of course, going towards the galactic core here, where it's extremely dense. Scutum star cloud, Sagittarius star cloud, and that. Have a look now while you can, because they will disappear relatively soon. But down in the southern sky, sometimes people think, oh, there's a cloud on the horizon. Yeah, it is, but it's not in our atmosphere. It's light years away. So have a look at that. And you can do this sort of stuff for yourself. This is one I took recently. This is just looking up into Cygnus, mostly at the North America and Pelican Nebulae, and you can see a lot of what's going on here. This is just a cheap lens and a DSLR camera on a little Star Adventurer tracking mount. I'd set the lens, I think it was about 150 millimeters, can't remember exactly. But we've got the Emission Nebulae around here. We've got the dark nebulae going in here, making the so-called Gulf of Mexico region in the North American Nebula. You can see the blueness around the brightest stars here. There's Reflection Nebula. You've got that dark nebulosity here. We've got the open clusters here. We haven't got any planetaries that we can see, or galaxies, or planetaries, galaxies, or globular clusters in here. But it's a really lovely region of sky, and you don't need to do exceptionally long exposures or anything like that. In fact, you can get quite a lot if you take very, very short exposures and stack them with a wide angle lens. You can get an enormous amount of joy from this. But start having a look at what's going on in and around the Milky Way, and you can start enjoying these fuzzy blobs and start picking up what they teach us about our stellar environment. So with that, if you're still there, thank you for listening.
Wow, Steve, that was the most space I've had in a long time. Well done.
Thank you.
That's a great presentation. Thank you so much. I'll be testing you all on it later. I like the really dark. like the really dark, fuzzy black. The black clouds of gas. They're so startlingly striking, aren't they?
Yeah. Well. I say, read Martin's article in the current. Let me stop sharing my screen. In the current Popular Astronomy, because he is so good on dark nebulae. So, yeah, and it's a really, really. I think it's probably the best article on it I've seen in a Popular Astronomy mag. So, go read it.
Well, I'm surrounded by the magazine, but I don't think I brought the correct one through. I'm in a new seat today. I'm kind of like hemmed in and can't get up and move. So I don't know where the magazine is, but it is out this month, isn't it? What's on the front of it? I can't remember.
Dark nebulae. It's all. Yeah, I've got mine's in another room at the moment. But yeah, it's all about dark nebula. So it's just absolutely fantastic.
Just entertain the troops while I go and get my magazine, Steve.
Ah, right. Entertain the troops. What do you mean do? A song and dance routine or something like that? No. There's a lot to see in the sky this month. In fact, they're all. But autumn, for me, is just a really fantastic time of year because we're getting. It's still warm-ish in the evenings. That's the one. Okay. But yet we've got the longer night, so we can observe and sleep, which we can't do in this. Well, I can't in the summer. One or the other.
So
anyway, over to you, Vic.
Thank you very much. This is our magazine that's out every 2 months. This landed, I think, only yesterday. No one's actually commented on the fact that I have mine addressed to Professor Vicky Duncalf. Has anyone actually spotted that on the mailing list? It's a highlight of my every 2 months when that comes through the letterbox. Now, look, our membership fee is going to be going up, I think, to £25 per year in October. So please renew your subscription now. It's still great value at that price.
Oh, it's fantastic. I mean, this has got to be one of the best subscription, best astronomy club subscriptions there is with what the SPA gives you. So yeah, go for it.
We do give you a lot, right, Steve? You're getting your song back now.
Oh no, I don't deserve it.
And better. Thank you. Everyone's saying lovely things. They were so quiet in that presentation. I thought they'd all gone to sleep.
Yeah, I thought they'd all either fallen asleep or gone, I'm not listening to this rubbish and gone away.
It turns out they were concentrating very hard or ironing.
Right. Anyway, thanks for the comments, folks. I really appreciate it.
Would you be able to go over flats and bio shots in a future live stream, Steve? Hopefully.
Oh,
next time
I'm not the right person for that. I'm really not that brilliant an astro imager.
Okay. Well, there you go.
I think. I mean, yeah, I can tell you what they are, but really, it would be much better coming from someone who lives this sort of stuff. I do it because I have to sometimes, but it's not the thing I ultimately live doing. There are some very, very good astro imagers out there, and bound to be some in the SPA, and I think it's much better to get one of them to do something, because they will be able to tell you so much more than a dabbler like I can. Right,
I'm going to play your song again, Steve.
Okay.
This time it's a bit. I played the version without subtitles. I like to play subtitles because you can't hear everything that I'm singing usually. So here it comes. Let's see.
Steve Tonkin the binocular astronomer. He believes that 2 eyes are better than 1, yeah.
It's
And
true
he's
though.
a dark sky warrior. Did you know that Steve is actually short for Stonkin? Soar round the heavens high, try his but the binocular sky. You won't believe either of your eyes, Steve Tonkin. Oh yeah. I can't believe either of my eyes, the left nor the right. What a view.
Vicky, you've just reinforced my notion that you're completely insane. Wonderful.
Thank you very much.
I thank you for doing it. I'm very flattered that someone will go to that trouble.
Hey, that's not bad, because considering I knocked that up and I didn't know you were going to be a guest until like mid-morning, that's not a bad day's work.
It's not bad, is it? No. Well done, and greatly appreciated. Thank you.
Thank you, Steve. Thank you. Right, listen, I have got a couple more pub quiz questions to ask. Do you want to help me moderate the pub quiz and you can extend on the answers?
We hope.
I've only got 5 little questions left, and I'm sure you'll be able to add a decent bit of stuff. Let's have a look. Okay. Right then. Well, you can talk a little bit about this one. It's a fastest finger first round. That's the only way we can play it, really, Steve. So I'm going to ask the popular astronomers, who is the first person to type correctly Zubin el-Ganubi? You know I love that star name. Zubin el-Ganubi. Which star's that, Steve?
Oh, it's one of the it's with Zubin el-Shamali, and it's one in Libra. Means Zubin el-Ganubi is the southern claw. Zubin el-Shamali is the northern claw. Libra is actually the old. It was ripped off from Scorpius. If you look at the if you look at the depictions of Scorpius, it's a scorpion with really wincy little claws. In order to get from 11 to the magical 12, they ripped off the constellation and formed the constellation of Libra from it. And so the scorpion's claws have become Libra, the only constellation that isn't in the zodiac that isn't a living thing. So it doesn't even belong in the zodiac, because zo from zoo means, it's the cycle of animals. And it's not an animal. So bye-bye, Libra. Go back to being Scorpion's claws, in my opinion.
Wow, there you go. Well, the Sky by Eye was the first one, and by looking by this, the only one who got it right so far. So thank you. Let's just open this window. Excuse me.
Yep.
Right. Oh, that's going to let all the insects in. They just love my ring light. Okay. Well done, everybody. Okay, next one. It's another spelling one. The first person to spell syzygy. What a great word. Syzygy. What's syzygy, Steve?
Syzygy is a wonderful hangman word, 'cause it's got no vowels, a bit like rhythm, really. Syzygy is the thing that goes along with quadrature. Syzygy is when you've got 3 bodies in a straight line, approximately. Quadrature is when you've got a right angle. So something like an eclipse of the sun or moon. Ray Ward's got it right.
Well done, Ray.
Only happens when it's a time of syzygy. It's a lunisolar syzygy with Earth. So it's 3 objects in a straight line.
3 objects in a straight line. Well done.
The S one, the Z one, and the G one, I suppose, with the Y showing. No, nothing to do with that at all.
Very, very good. Okay, so Ray Ward was the first person to get that right. We've had a couple of wrong spellings, but I think, that's Mr. Oh, God, I'm cross-referencing it. Syzygy. Oh, no, wrong there, I'm afraid. And Zizygy, wrong. Ray got it correct. Well done. Thank you, Ray. Okay.
Ziggy Stargusty. No, sorry. No, I'm going on them.
Next question is a Pop Astro question. Who is our wonderful, lovely, devoted citizen science officer? Do you know who that is, Steve? Don't say it. the equivalent of coughing in Who Wants to Be a Millionaire. Right, I'll do another one.
sorry, Mrs. Sheep Tender.
We'll see who is our citizen science officer. Oh, let's have a look. I might have to wait for the correct spelling actually to come through because you've got it wrong, David Egan. Oh, well done, Tim Crook. Is that the correct way of spelling it? Alice Shepard. Yeah, there we go. It's Alice Shepard. Well done.
I just spelt that wrong.
We love Alice, and she diligently compiles the most excellent citizen science, and she usually appears right at the start of the magazine with her lovely chatty column. There she is. This week, this time it's about what are foxes' fires? Don't know what they are. Anyway, there we go. A good article this month. And it's definitely not Krempog. Okay, so can you spell the town she now lives in Sweden for 1 million bonus points? I can't actually. Can you, Mr. Morrow? Can you? Okay, next question. Question number 4. Must remember which way round to do this. It's the right hand. Whose middle finger is on display in a museum? Nearly did that back to front then. I would have not been broadcasting again if I'd got that back to front. Do you know the answer to that one, Steve?
No.
Oh, don't you? I better get a quick Google it quick.
I'm not going to Google it. I'll learn from the answer will come up eventually. Somebody's saying there's a few answers coming up there. Yeah. I'm also just going through the comments when I was giving my talk. Some very, very good comments there. I'm sort of learning a bit from those as well, which is great. It's what's so great about doing these things, Vicky, is that you know there are people who know bits that you don't know, and they're sort of, and you learn from them, and it's wonderful. So such a lovely.
I tell you what, I don't know who is mysterious Mr. Numbers, because he's racing home on the quiz tonight. He's not only got the fact that it was Galileo, but his it's in the Museum of History and Science in Florence, so he's got multiple questions right.
Well, isn't that great?
It's quite a macabre picture, actually. It's just an awful. It's like a little glass cloche. Not a nice picture, really.
Yeah, there's a pub in near Edmonton in Alberta in Canada where there's a toe.
Oh.
I won't go any further.
Mr. Numbers is seeing Galileo's middle finger. There you go. That's quite the thing to see.
Yeah, but the question is, who was Galileo flipping it to?
Yeah, who is Galileo flipping it to? Sorry, I'm getting messages coming through on my phone. Naughty girl. Yeah, who is he? I think they took bits of him and then they went up for auction. Let's have a quick look here. Google's telling me everything. The museum directed that the thumb and middle finger from Galileo's right hand had turned up at auction and were recognized as being the finger of the scientist. They're now displayed in slender glass cases.
A bit like Jeremy Bentham, really, isn't it?
Ooh, what's Jeremy Bentham?
Oh, Jeremy Bentham, University College London. I mean, his embalmed body was at one point I might still be for all I know, in the atrium in a glass case.
Oh, nice. That's a nice welcome. We've got one more question. Well done, Mr. Numbers. I think you're on 3.5 points now because you've actually been to see it, and that's definitely worth an extra point, half a point. There's somebody watching this who's going to know the answer to this straight away. What happened on Steve? Remember, you're not answering these. What happened on February the 28th, 2021? What amazing astronomical event happened? Do you know what it was, Steve?
Not allowed to answer.
Yeah, you're not allowed to answer, but just give me a nod if you know.
No, I don't.
That's all right then.
I may know the event. I don't know what happened.
So what? Jeremy is still there. We walked past him. I'm going to have to Google him. What's he called? Jeremy Bentham?
Bentham, yeah. In the comment below that, Ian Baker's comment, you got the surname spelled. David Deegan has got the answer to yours. Yes, it is there.
Is that his real body there, sat up? Jeremy Bentham? Sat up in the glass case?
Yeah.
They've done a good job on him, to be honest. He's done a good job. He's done a good job. Yes, okay.
Well, you know, come on. The Egyptians have got this sorted, haven't they?
He doesn't look too decomposed. David, well done. The Winchcombe meteorite fell, which some of our lovely ERO team found bits of. Derek, well done. And Adam and Jason, well done on that. There's also a pub named after him. Well done,
Yeah.
Kat.
And round about the same time, there's one fell round here. I live between New Forest and Cranbourne Chase, and there was another one spotted, and coming a fireball coming down. Okay, meteorite landing, and the area in which it's landed has been narrowed down to about 300 square miles. No, I'm not going out looking for it.
Hey, his bones are dressed, his head is preserved but not on display, so maybe it's not his real head. I'm sorry, I get me Woodman coat and Winchcombe mixed up, Adam, but well done on that sensational find of yours. Thank you. Right, okay, we've got one last little thing to do this evening, and then we're going to clear off because we have had a long one tonight. If we'd have had Sonia on, this show would have been 2 hours long. We're going to try to stick to an hour in the future. It's a wax head. I thought he was looking quite perky. Thought he was looking perky.
Madame Tussauds. Huh?
Yeah, he was embalmed, but his face was wax. His actual head was on display. Oh, so it's just, oh God. Oh, that's macabre.
Yeah.
That's macabre.
Thanks, Robin. It's good to have the proper thing. I mean, I haven't heard anything about Jeremy Bentham's. I was at the conflicting, you know, the competitive college. I was at King's.
Oh, were you now? Were you now?
Yeah, which I really shouldn't have gone to, but it was the only one that did the course I wanted to do. But UCL is much more my sort of place, really.
And I tell you, is Cosmo your sort of sloth, Steve?
You see, I wouldn't have thought Cosmo was a sloth.
I think he's a sloth.
I think you're right. I'd have thought Cosmo was a slow loris.
Oh, I never thought. He's not sure now. You've got him all muddled up.
I'm sorry. Is he having an identity crisis?
He doesn't have venomous elbows. I'm fairly sure that's a sloth. That's a sloth.
Okay.
That is a sloth. That's what they do, isn't it? They hang. Anyway, Cosmo, whatever he is, every week he goes to a different place in the solar system. So we'll play his little song, and then I'm going to read out just a couple of clues, and then we'll see who's the first person to guess it. Okay, here it comes.
He's been flying around the solar system, or maybe a bit further.
But to the casual observer, he's a mithering, pestering sloth.
Where have you been to this week, Cosmo? Cosmo, where have you been?
3 clues. Only answer after the clues. Cosmo over and out. Great. Okay, so we've got 3 clues. I think they're a bit rubbish, these clues are this evening, but when you've made a song and devised a pub quiz in one day, you kind of just start flagging a bit, devising a whole show. So here it comes. Okay, Cosmo. So every week, Cosmo clears off, he escapes out and goes on a little adventure, Steve. This little play, you're not guessing this, Steve. Don't forget that. I'll show you my middle finger. Okay, I know you know everything, Steve, so...
I don't.
Okay, it's a little... Go on.
No, I've been known to be wrong, and both times I've admitted it.
Even Cosmo thinks you're funny. Right, okay. It's a tiny little place. It's only got a radius, that small, a radius of only 3.9 miles. It's so small. The Cosmo nearly fell off the edge of it. It was discovered by the American Asaph Hall on the 12th of August, 1877. Oh, he got it. He's got it. And it really gets a clip on, though. It only takes just over 30 hours to orbit its parent planet. Right. Where's Cosmo been this week? It's tiny. Its radius is hardly just 4 miles. Discovered in August the 12th, 1877. Oh, no. Sky by Eyes got it wrong. Who's going to be first to get it right?
Well, David Deegan's got it right.
He's got it right, hasn't he? Oh, but I love seeing all the answers come in. We'll give them time just to flex their little mental muscles a little bit. Ooh, oh, Ian Morrison got one wrong. I'll be rubbing your face in that all weekend.
Phoebus. Ian, Phoebus is the sun. Bright Phoebus, arise like the sun in the sky.
Ooh, quite
with
like
her
that.
red rosy cheeks and her sparkling eye. No,
Yeah,
don't give up your day job, Tonkin. Yeah.
What's that? Cosmo says, leave the music to Vicky. No, that was lovely. Ian, I shall shame you. I shall shame you when hopefully we'll see you at the weekend. Okay, everybody, the answer was Demos, and David Deegan got it correct. Well, the unequivocal winner of the quiz is a mysterious Mr. Numbers, who I can only see a tiny little glimpse of the thumbnail of his picture. Who is Mr. Numbers? We might have to pull his mask off and reveal him. And I think that's all for. I thought it was going to be a really quick, easy, light show tonight, and instead it's 20 to 10. So thank you to everybody who stuck it out. You've all been amazing tonight. Thank you to everybody who competed in the quiz. Thank you, Mr. Tonkin, for coming on at short notice. And
I hope I didn't go for too long and drag it out. But hey.
That's all right. Yeah, it's kind of subtle hint. I must remember to tell everybody it's about 20 minutes next time. No, it's great, Steve. Your presentation was fantastic. Thank you for going so in depth. You've put a lot of effort into that. Jed, first class show. Thank you. Oh, thanks, Sandra.
It is. It's always fun to be on here, Vic. But it's often at times I can't do so.
Oh, thanks. That's lovely, lovely. Right. Okay. We'll give them 10 seconds to put in a couple of last comments, because normally when I switch it off, all the ego boosting comments pop up after they've gone and I can't display them and I don't get my little ego fix. It's quite terrible, actually. Thank you, Bob. Lovely to have you on as one of our regulars. Thank you. Thank you, Ian. Yeah. Thank you, Ian, our lovely regular. Oh, Kath. Lovely. Oh, hang on. We need to launch Cosmo to his next destination. 5, 4, 3, 2. Oh, double bounce. He pranged off the bookshelf. Ooh,
into the waste paper basket. Oh, cruel woman you are, Vicky.
Oh, I am very cruel. I'm cruel. Okay, everybody, good night. Please share the video once more, and I'll catch you all later. Thank you, Steve.
Night. Good night,
Bye.
everybody. Thanks for having me again.
Thank you, Kiri. Bye, everybody. Bye. Bye.